organize the questions loosely based on themes. We can start with questions related to space and astronomy. I think this would be a popular question for all school kids. This was asked by Saugata from JTV Hebbal, and they're asking what is a black hole? Oh, it's KV. Sorry. The question is, what is a black hole? Is black hole and Big Bang theory related? I mean, are they related? Does time stop during traveling inside a black hole? What is a wormhole? When we travel through a wormhole, will we die? During traveling in a black hole, can we time travel? And there was another question related to black holes and wormholes. What is a wormhole and is it true according to you? How do we come to know that there are more galaxies like Milky Way? So Shiv.
Okay, so I am Sumati Surya. I work in theoretical physics in the area of general relativity, where we talk about things like black holes. Okay, so I think that one of the black hole questions is simply, what is a black hole?
Yeah, what is a black hole? What is a wormhole?
So black holes are basically, astrophysically, they're collapsed stars, and they're regions where if light goes in, it cannot come out. So light is trapped inside these regions. In the theory, Einstein's theory of gravity, basically what happens inside a black hole is there's some place where space-time becomes very, very attractive, or it starts to crush things together until you reach what's called a singularity. And that's where it's sort of similar to Big Bang physics, where you say, when you go back in time, you go back to a time when things are there's such a strong force, gravitational force on you, that you basically collapse and you get to the singularity. That's early back in time. So they're related in this way. Does that make sense to you? Does that make sense? Or do you have any questions about what I said? Because it may have sounded a bit more technical than you are used to. So imagine something that's pulling you really, like very strong gravity. So we know that on Earth we have a certain amount of gravity, right? And if we went to Jupiter, would we have more or less gravity? More, right? So we feel the force of gravity a lot more, right? Even though we're the same mass, we'd feel the force of gravity. So in a black hole, yeah, go ahead.
Ma'am, maybe feel the force from all directions or one direction?
You feel it towards the center, just like we feel it towards the center of the Earth.
And in black holes,
Yes, so it will be towards the center of the black hole. And what happens inside a black hole is basically that the way we think of space and time will change as you near this place, but we don't understand what physics goes on there, which is called a singularity. Okay, so it's something that we're all trying to understand what happens near a singularity. But it's basically, you can think of it as very, very, very strong gravitational force, which will basically, collapse us, make us very, we won't be able to retain the shape we're in and so on. So we can think of what they call tidal deformations that would happen inside the black hole as you're going towards the singularity. So somebody also asked, what is a wormhole, right? So wormhole, can I just quickly draw it on the board? It's just a very little, okay, you can think of the wormhole like this. So you have a door there, right? The door there, it opens out, and you walk out of there and you come out back here. So that's kind of an example of a wormhole. It's connecting up parts of space, in this case just space, which you would think are very far apart, right? So wormhole, typically you can think of something where you're taking a handle of a cup or something and you're sticking it on this. That would be that's how you would describe a wormhole. But you could also have a wormhole that goes from one time to another time. And then they talk about how you can build time machines with wormholes and things like this. I don't know if I answered the question. Yeah, something.
Yeah. The student wanted to know if Big Bang and black hole are related, and if time travel can happen.
I mean, time travel, I think, so she has already answered that question. Big Bang and black holes are not necessarily connected, but she did point out that there is a connection about singularity. The black hole is about a singularity at a point. Big Bang is a more complicated singularity, but yeah, it is some kind of singularity. It's in classical galaxies. There was also a question about galaxies. How do we know there are galaxies outside?
Yeah.
That was one of the questions. How do we know there are
How do we know there are other galaxies other than Milky Way?
That's not easy. So for that you have to actually know. We have some idea of the lengths involved in Milky Way. We are around 8 kiloparsec from the center of galaxy. Kiloparsec, so 1 parsec is 3 light year. Light year you know, right? You have some idea about what light year is. So 1 parsec is 3 light years. So we are from the center of our galaxy, we are around 8 kiloparsecs. So multiplied by 3 around 25,000 light year, right, from the center. So we have some idea how large our galaxy is. We can estimate distance to various objects around us. And from 1920s, people would do it and see that some of the objects are very, very far away. Right? They are not part of our galaxy. The nearest galaxy is almost 700 kiloparsec. That is around a million light years away. So that's very far away. So that is how we know we can measure distances. We know the lengths in our galaxy. We know that we are roughly only 10 kiloparsec from 30,000 light years. That's how this extent of our galaxy. The nearest galaxy is very, very far away compared to the size of our galaxy, almost a million light years. And then we can find, we have found galaxies all the way to a billion light years, right? 1,000 times further than the nearest galaxy. So that is how. But how you actually find this distance is a very technical subject actually. So I'll not tell you. But that is how we find it. So it's not easy. It was only done in 1920. So it's a very good question. Because only in 1920s people knew that there was a world outside our own world. That means our own galaxy. It wasn't easy to do. It took a fair amount of effort. There were a lot of debates between astronomers. Whether what were called nebula or part of our galaxy or they're outside the galaxy. But now it's established they are outside the galaxy. Sir, have I answered all that?
Yeah, since you have the mic shift, can you also answer a question like how can we count the number of stars in the Milky Way and how many planets there are and how are galaxies formed in general?
Okay, how you find stars is the same way as you find galaxies. Like the point is distances to stars is also difficult to find. But generally stars are point-like, so they shine in a certain way, so we are able to figure out that they are a part of our galaxy. Right? But again, it's not easy to tell a star from a galaxy when you're looking at very, very faint sources. But mostly we are able to tell. So just the way you form galaxies, you can find stars. So planets is a very difficult subject actually. You see how many planets there are out there is it's a very, very difficult question to answer. There was no extra galactic planet, extra solar planet known to us until 30, 40 years ago. Now, if I'm not mistaken, I don't know the exact number, you can find there is a Kepler satellite which has found thousands of new planets around the star systems. Okay. I don't know the exact number is updated every day, I think, so you can actually take a look. Maybe that number is 7,000, 10,000, but how many are there is an impossible question to answer. Right? Because there are close to 10 billion stars in our galaxy. Right? You know, I mean, far, far away. But maybe 20% of star systems have planets. Right? And they may have multiple planets. Right? Earth has multiple planets. It's a very difficult question to answer. What we can say is, so far, thousands of planets around solar like systems, planet systems, stars have been found, and they will continue to be found. Maybe some of you will grow up and find new techniques to detect planets. It's not easy to detect a planet outside again. So yes, so the whole point is one way detect a planet. For instance, I'll give you one example. Like there are 2 or 3 very big techniques, but the simplest one is if a planet is going around the star, right? And you are looking along the plane. Okay. So what it do is planet will occult the star for a while. Block light, right? And that blocking of light would be a periodic signal, right? You see my point? The periodically it gets dim and it lights up again. And the periodicity is related to the time period of planet around the star. This is just one technique, and this is not the best technique. The best technique is based on atomic physics actually. A certain line and the shift is built. Best in the sense, this technique only works if it is intercepted along your line of sight. Otherwise, you can't do that, right? The orbit is not like this, but like this. Then you can't use this technique. So these are some of the techniques that are used to detect planets actually, and it's a very active area of research currently. And people like you will grow, might develop new techniques, and you will know that so far, Earth-like planets are very difficult to detect for this reason also. Because the whole point is they do not cause that shift, but they are not massive enough. Jupiter-like planets, you see, if you look at the list of all the planets that have been detected, you will find more massive planets. You might wonder if it is a fair sample, it's not a fair sample, right? You may have more Earth-like planets, which are very difficult to detect. So yeah, you can detect planets, and it's an ongoing area of research, very exciting area of research.
Thank you. And how are galaxies formed?
And how are galaxies formed? We do not have a clear answer to how galaxies form. We have a theory of how galaxies form. So galaxies are formed because of some conditions in early universe, and that leads to gravitational. So what you call gravitational instability, it's a bit like this. If you take a mass of gas and make one part of it more overdense as compared to other, right? That is unstable. That collapses onto itself. So I'll give you a simple example. If you take sun, for instance, you know sun is stable, right? It's stable for billions of years. But if you take out the energy, for instance, it stops forming energy in the center, right? Then there is no pressure balance. So the whole point is there is only a gravitational infall. And it takes 5 minutes to fall to the center. There is nothing else to prevent it. Something else will prevent it. So this gravitational instability is responsible for formation of galaxies. How exactly it forms is not known to us. Exact mechanism is still a bit of a mystery. But there is sufficient evidence that gravitational instability of gas, almost near to homogeneous gas, long ago, as starting from initial condition, that's how galaxies form.
Okay, thanks. In the next, I got a bunch of questions related to being a scientist and about scientific thought in general. So Abdul K has asked how to be a successful scientist. And on the same lines, a student has asked what was the key to success of CVrahman and what qualities as a student we need to apply from CVrahman's life.
So I'm Sadik. So the question was first, what I mean, of course, if you ask different people, all of us will have slightly different variations on what it takes to be good at science. Okay, let's not say successful scientist or whatever, but what it takes to be good at science. And the most important thing is that you have to have the ability to question without, and question in a very ruthless manner. Till you do not have a satisfactory answer to your question, you keep asking the same question, maybe in different ways, maybe you try to answer that question. So the process is not just, it doesn't end at just asking the question. You should answer the question. Now, how do you answer the question? I mean, you can say, why is the moon a ball of cheese? That's a question. But there's a method of answering that question which is contained in science. And science has a very constrained way of it prescribes certain method. Okay, it's called the scientific method, and this is based on logic, reasoning, and evidence. Okay, so you have to apply. So you work with a framework. You say, okay, I take all these things for granted because somebody else has checked all these things, and I have enough reason to believe that what is written in my book after that person has checked, it's all okay. So now you start in that. So that's one place you can start. And then you start asking your questions, okay? And you start getting answers. If your answers, so you can often start with a hypothesis, okay? You can say, all right, maybe if I have this mic and if I release it, will the mic go up or go down? The question depends on which way gravity is. Okay, on Earth it will tend to fall. But the point is that there could be some situation in which things may float out. So you have to ask the question in the context, and you have to have the ability to criticize. Remember, every generation of science grows on the back of previous generations, and often while it is adding to the knowledge acquired in previous generation, it is also often in conflict. And the bigger discoveries in any generation are almost always in conflict with the understanding of previous generations. So, the idea is that you should question, you should know what is the foundation. It is very important to know the foundation. If you want to do hard sciences like physics or something of that sort, then a mathematical ability, to cultivate a mathematical ability is extremely important, because mathematics is based on a logical premise, which is what science actually takes advantage of and builds forward. So, so sometimes you do not necessarily have a very clear understanding of where the physics is going to take you. But you can solve a certain situation mathematically, and you solve it for a certain, and you get a certain solution. Maybe you do not, when you did that solution for the first time, you do not necessarily understand what you are going to get. You do not even have a proper expectation. But once you arrive at that solution, you can then interpret that and then build your understanding backwards. Okay? And so it's a process. It's not like somebody just comes out of the blue and just says, okay, I will see why the sky is blue and why things fall to the earth, and it's not like there is a whole bunch of questions. The most important thing in science, at least this is my experience, is to ask the right question. Often when we ask questions, we are confused about the framing of the question. You frame your question properly, the chance that you will succeed at answering that question will increase dramatically. It requires a certain clarity of thought to ask questions with precision and in the framework. So you can always ask a question which is beyond science. Like right now, a question like what is consciousness is something which is right now beyond today's science. It may be something which tomorrow or whenever people may advance towards, but that is beyond science. So you can, that's too big a step. Okay? First, you can start by understanding what your brain does. Okay? And then you have to understand what the cells do, how the nervous system works, how it all connects up, and you build like that. So so this is in some sense what I've tried to do, is to describe the process of science, of doing science. So you have to really keep an open mind. Everything can be challenged, but you have to challenge it right. You can't just challenge it because you don't like it. That will get you thrown out of the scientific seriousness circle very fast, because scientists do not want to abandon what they have accumulated over generations. Okay? And they are not fools. So you have to work very hard in order to make the change. This is very important. Okay? And so far as CVrahman goes, you are an exceptional person. He worked extremely hard. He spent he was a civil servant, and after office hours and before office hours, he used to go to a scientific institute to do science. And this was when he was, I don't remember the position he held actually, but he was, I think, very high civil service position in Calcutta, where he negotiated with the local institute there, cultivation of science, which he used to pass, to actually do work. So, he not only did he work, do his day job, he did a night job. His night job was science. And this is what it took. But here is a remarkable person who had great acumen. He had a great feel for science. He had a certain way of thinking about nature. If you look at Rahman's papers, what you will find that he has always taken his inspiration from his observations of nature. And there's a museum down this thing, I do not know whether you got a chance to see it. But you can see he has collected many things, and he has asked, why is the color of this thing this? And why is this shattering, why is this glass shattering from inside rather than from outside? And so on and so forth. So that's not the only way you do science. But this was how he did science. Okay? So he picked up from observations, he had questions, he questioned his surroundings, and he sought an explanation through precisely constructed experiments. And some of the instruments that he created in order to do those experiments were really works of genius. As instruments. Anyway, I think I'll stop here and somebody else can do something.
Another question this is open for all the panelists. Another question that students are interested in is, how do you actually become a scientist? What is the career path you need to take? What are the degrees you need to have?
Well, the typical path to become a scientist in our educational system is to, after you finish your 12th standard, then you choose science as your topic, which is like you go for a bachelor's degree, or in most places now you have a 4-year degree, which is a bachelor plus master degree. And after that, if you really want to practice science, then you do a PhD. Basically, PhD is that the process is that you join some lab or a group, okay? So, and then you work with somebody or a group of people, and you learn the practice of science. That is when you actually start practicing science yourself. Till then, you are learning the foundations, you are learning various, like somebody said, mathematical tools which you may need, and the basic information and so on. But you may have done some lab experiments, but these are mostly experiments where you're supposed to do something which somebody prescribes to you, and then you more or less know what result you are expected to get and so on. But once you go in for a PhD, you're working on your own problems. Some of the questions you may be asking here, and like Shiv said, some answers are not known, and you are seeking these answers. So the real practice of science begins from the time you start doing a PhD. There are exceptional cases where people have not gone along these paths and still have become successful and so on. But this is by and large this is the rule. Was it?
Yeah, I think that
Okay.
that helps. And yeah, I just want to add that a lot of institutes offer summer programs which offer students hands-on experience on different telescopes or experiments. So that is one thing that I wish I would have done when I was a bachelor student. Okay, moving
So one
on.
thing which a lot of you can do at home is, nowadays because of internet and YouTube and all that, there are a lot of experiments and stuff you can do at home with things which are available in a kitchen, or simple things you can buy on Amazon and so on. So you people are at a big advantage that you can start playing with things much more easily than our generation could.
Okay, so the next set of questions are just general science questions. Renal wants to know, in the clouds, why do charges get separated? Is it because the positive charges are lighter and the negative charges are heavier?
So you see, this is electrostatics of atmosphere is not. I mean, it's not an entirely, again, it's not an entirely straightforward question, but one thing is definitely known, that is separation happens in clouds. But you see, there is always, when the air is lifted, there is a charge being deposited into the cloud also. So there is a cycle actually. Lightning strikes, charge comes down, and then it gets lifted. In cloud, the charge separation partly happens for the reason what somebody said, that it's heavier. But sometimes it could be oppositely charged also. So we do not really know that much about how electrostatics in clouds happen. But it's a fact that the Earth cloud system, I mean, it's electromagnetically, see, there is roughly, if you actually see the potential difference between us, is around almost 200 volts. Of course, we are in equipotential surface, we don't get a shock because the whole point is we are standing on Earth, so it will not happen to us. But this is a very active system. I mean, during the day, the charges, like during on a dry day, right, they get lifted and they get deposited. And at night time, I mean night time, or generally when it rains, right, there is either a drift below, or generally lightning. I think, like, I don't remember the numbers actually, numbers I'm forgetting. How many lightnings happen each day on Earth is, this number is known. So we have a rough idea how much charge is brought back to Earth through the lightning. So it's a system, it's a cycle, and that's what you have to remember. I myself don't know more than that actually for what I have told you. Because from what I know, this mechanism is pretty complicated of separation of charges. Because there is humidity and there is the water molecule, the way it gets polarized, then it separates the charges. It's a complicated phenomenon, to the best of my understanding.
Thanks, Shiv. A couple of students have asked, how are magnets formed? How are magnets formed?
Okay, so if you, for instance, the easiest way for you to make a magnet is to take a battery and connect a loop of wire. Okay, look, if you just connect only a copper wire, you will short the battery and that's not going to be happy. So you put a little bit of resistance or whatever it is, okay, and you run a current through it. When you run a current through it, what is happening is that the charges are moving in one direction, okay, and therefore that creates a magnetic field which is going to circle around the lines of equal magnetic field, okay, are going to be circles around the tangent to the charge, to the motion of a charge at a point, okay, and then you have to make all these surfaces, and you will get how the charge. This is the easiest way to make a magnet, but I suspect you are talking about ferromagnets. So now there is essentially three very kind of common classes of magnets which we know. I mean, there's paramagnet, there is diamagnet, and there is ferromagnet. So have you heard of Faraday's law? Right. So not everybody? Oh, okay. So it's a bit like this. So Faraday's law. Okay, then let me not couch it in terms of law. So if let's say I make these currents, okay, I create a magnetic field. So I can make a coil, okay, I can make a nice magnetic field, okay, in some direction. Now if I put some chunk which is not magnetic inside, what will happen is that this chunk has little atoms inside, okay. It is made out of, it has many other complications, but there is a crystal, the crystal is broken up, it is, there are little crystals which happen, but so there is a lot of complexity out there, but finally you can see that there is atoms. Now each of these atoms has electrons in it, so you can think of the nucleus as relatively stationary. It is not doing too much motion. Whatever motion is happening is back and forth, which is not necessarily doing too much for the magnetism. But if you look at the electrons, okay, the electrons are moving in some orbit, like planets in a solar system, and so they pose a magnetic moment. And so now what is happening is that you put a overall magnetic field, and so now you have a little magnet in each of these atoms, and this magnet tends to follow the direction of this moment, of this field, and so that is your paramagnetic response, okay, to the atom. When you apply a field, you tend to put the magnet in that direction of the field. That is called paramagnetism. Diamagnetism tends to oppose the direction, okay. I'm just giving it to you. It's a little bit more involved to explain, but it's okay. And then ferromagnetism is something very peculiar. It happens because there are all these domain structures, etc., which you have in a magnet. So there are little crystals all over the place, and if you start with a ferromagnetic material and you do not put a magnetic field on it, then there will be no magnetism to that material. Now you put it in a magnetic field, it kind of starts aligning. But now because you have coerced it, you have actually pushed it, and it has permanently formed, because it is all these little things which are there tend to lock its ability to relax back into the old configuration. So when you subject it to a high enough field, you will magnetize it. So if you put the iron in this current coil, you will magnetize it, and then if you want to demagnetize it, you have to put it in an AC coil. If it's a DC coil, you will. But if you might have done this experiment, if you put it in AC current, then it basically what it's doing is it is putting the electrons this way, and then half a cycle is putting the electrons the other way, and so on and so forth. And then what you will do is, while this AC current is happening, you will dial down the current so that essentially it's going with lower and lower amplitude, and you will finally go through a cycle of demagnetization of this particular thing. The other way to demagnetize a permanent magnet like a ferromagnet is to heat it. If you heat it, everything agitates, and then everything becomes more random, and that's how you. So these are some of the ways you magnetism.
Right. Thank you so much, Alex. Sadly, we have to cut this short. Thank you, panelists.